What if everything you see, everything you are, isn't fundamental? What if the solid world around us, the planets, the stars, even you and me, is just an illusion, an emergent property of something much, much deeper? Well, today, we're going to go on a journey from a kind of philosophical mystery to a very real scientific theory that might just explain where reality itself comes from.
So let's just dive right in. For the last century or so, physics has told us a pretty simple story. The world is made of tiny little things, fundamental particles, electrons, quarks, photons. But what if that's not the right way to look at it at all? What if the universe isn't built on things, but on patterns? To even start to wrap our heads around this, we have to talk about the vacuum of space. You probably think of it as just, empty, nothingness. But quantum physics sees it completely differently. Even in its absolute lowest energy state, what we call the vacuum, there's this baseline energy humming away. It's called zero-point energy. It's the energy that's left over when you've taken literally everything else away.
And that's why you often hear it described as a seething sea, and honestly, it's a perfect analogy. This is not some calm, quiet place. The quantum vacuum is a chaotic, restless ocean of energy fluctuations, with virtual particles popping into and out of existence all the time. It's the ultimate canvas of pure potential.
Okay, so that brings us to our first big idea, harmonics of reality. Because if the very fabric of space is this chaotic, seething sea, then how on earth does the stable, predictable reality we all know and live in emerge from it? How do you get order from that much chaos?
I mean, that's the core puzzle, right? If the background of everything is fundamentally restless and random, why isn't the universe just a blur of energy? Why do we have these incredibly stable, predictable particles like electrons and photons that become the building blocks for, everything? There has to be some kind of organizing principle going on.
Well, here's one incredibly powerful idea. Maybe particles aren't things at all. Maybe they're just stable patterns that manage to survive in all that background noise. Think about it like the harmonics on a guitar string. You pluck it and it vibrates like crazy, but only very specific, stable frequencies, the notes, are the ones that you actually hear. Or picture a stable knot, like a little whirlpool forming in a fast-flowing river. The particle isn't the water itself. It's the stable shape that the water takes.
And this whole concept has a name, constraint-resonance. The basic idea is that there are some deep, underlying rules, constraints, that act like a filter on all that chaos in the vacuum. These rules only allow very specific, stable patterns, these resonances, to stick around. So in this view, chaos gets tamed, and what's left behind are the stable particles that build our entire world.
All right, so let's move on, because this is where things get really wild. This whole idea isn't just a fun thought experiment. No, it might be the key to unlocking one of the absolute biggest mysteries in physics. We're talking about gravity's two-way secret. And here's the big reveal. This whole way of thinking, it's not a metaphor anymore. It is the absolute core of a formal scientific theory called CRET, that's Constraint-Resonance Emergence Theory. And it uses this exact logic to argue that gravity itself isn't a fundamental force, but that it emerges directly from this whole process.
Okay, so let's break down how CRET actually pictures reality. Think of it like it's built in 3 layers, from the ground up. At the very bottom, you've got the microdynamics. These are like the fundamental pixels of space-time itself, maybe something like tiny quantum bits. Then, in the middle layer, the mesostructure, you've got quantum entanglement weaving those pixels together, making connections. And finally, at the top, you get the macro constraints. That's the smooth, classical space-time that you and I actually experience. Now, the engine that drives this whole theory is a really powerful two-way feedback loop. So information flows upward as the entanglement between all those tiny pixels builds the large-scale shape of spacetime. But then, and this is the secret sauce, information flows back down. That big shape of spacetime actually imposes rules that decide which entanglement patterns are even allowed to exist in the first place. The whole thing becomes a self-creating, self-regulating system. So you might be wondering, when does gravity actually turn on in a system like this? Well, Cree proposes this incredibly simple, elegant condition. When the gain of the upward information flow multiplied by the gain of the downward flow is greater than or equal to 1, that's it. The feedback loop becomes self-sustaining, and at that exact moment, space-time begins to gravitate.
1. That's the tipping point. The whole system's total gain hits 1 and it just locks in. And the part that is absolutely mind-blowing is that when you work through the math of this resonance condition, you actually derive Einstein's equations for general relativity. Gravity literally emerges from the feedback. It's not fundamental, it's a consequence.
Okay, this is a beautiful, beautiful idea. But is it actual science? That's what brings us to our final section. From theory to test, how could we possibly know if any of this is actually real? Now, Crete doesn't exist in a vacuum. It builds on other really brilliant ideas, like entropic gravity, which also views gravity as an emergent thermodynamic force. But what Crete brings to the table is crucial. It identifies that precise gain equals 1 tipping point, and, most importantly, that two-way information flow. It's not just stuff bubbling up from the bottom, it's the entire system regulating itself from the top down and the bottom up. And because it's a real theory, it makes real, testable predictions, things we can actually go out and look for. For example, CRED predicts that gravity itself should be able to transmit quantum entanglement between two objects. And get this, it predicts the rotation curves of galaxies without needing to invent dark matter to explain them. It also suggests space-time should have a kind of memory or hysteresis, where it relaxes slowly after you disturb it. You know, the mark of a really good scientific theory isn't just that it makes predictions. It's that it tells you exactly how it could be proven wrong. For CRED, if we ever found gravitational attraction without a corresponding change in entanglement, or if we found a massive object that could bend space but couldn't be entangled by space, that would break the theory. This is what makes it a real, robust scientific proposal.
So if we're going to put this all in a nutshell, it's this. What we call the curvature of space-time, what we experience as the force of gravity. It might just be the stable, self-maintaining shape of this beautiful two-way resonance between the quantum world below and the classical world above. And that, of course, leaves us with one last truly profound thought to chew on. If the fabric of space-time itself is just woven from the threads of quantum entanglement, and if all the particles are just stable resonances in the vacuum, then what exactly is reality? Is it possible that everything is just one grand self-sustaining pattern of pure information? It's definitely something to think about.